All right, so this is going to be our first tutorial on stochastic processes. In our previous tutorials, we were just looking at some reviews of preliminary topics that were essential to help us understand stochastic processes. Okay, so this is going to be the first tutorial, and by the course of this tutorial, you should be able to define stochastic process. Also, you should be able to identify the specification of stochastic processes. Thirdly, you should be able to identify some classification of stochastic processes. And finally, you should be able to solve some examples, okay? So let's begin with the first session on definition of stochastic process. So what is a stochastic process? Now, the word stochastic emanates from the Greek word stochazetai, which means to aim at or to guess at, okay? So by definition, a stochastic process is a family or collection of random variables that are indexed by a parameter such as time or some space, usually denoted by this, or it can be denoted in this one, where capital T is the index set of the process, also known as the parameter space. Now, take note that in this tutorial, we are going to consider our parameter space to be a time component or factor instead of a spatial component of factor, okay? All right. Now, another thing that you have to take note is that a stochastic process is also known as a random process, okay? So sometimes if it's a random process, it's the same as a stochastic process, okay? So let's take an example. Consider the experiment of testing two electronic components such that when an electronic component is tested, it is either defective with the notation D or non-defective with the notation N. So the sample space of this experiment may be written as shown below. So we can have the first two components to be non-defective, or we can have the first one to be defective and the second one may be non-defective, or we can have the first one to be non-defective and the second one may be defective, or we can have both of the components to be defective, okay? So let X index T denote the number of electronic components that are defective on a given day. Now, if you recall from our previous tutorial on random variables, we used the same example where the random variable X was the number of electronic components that are defective, okay? Now we have X index T, so there's a time factor here. We want to observe the number of electronic components that are defective in a given day. So basically, we can show that X index T is a stochastic process as follows. Okay, so we have our sample space, we also have our range here, and we have our random variable which is now indexed by parameter T. Okay, so normally we write this in this one, we try to hide the omega, that's the element in our sample space, and just show this, okay? So we know that the elements from our sample space, if you have to replace omega, don't forget that this is like a function, it's a machine, okay, it's a function. So it has been designed to generate the number of electronic components that are defective, okay? So if we replace omega with this element, it gives us an output of 0 because it cannot detect any defective components, okay? If we replace omega with these two elements, it's given us an output of 1 because it can now detect one defective component in each, okay? And once we replace omega with this element, it gives us an output of 2, so it can now detect two components that are defective, okay? All right, so we can basically represent this process in this form, okay? So these are the possible values that we can observe, okay, once we perform this experiment at any point in time, okay? So this is the starting day, the first day, the second day in that order. We can also represent this in this form. So this is basically shown as the number of electronic components that we observe on the first day, which can assume these values. And this is also shown as the number of electronic components that we are going to observe on the second day. We can also assume these values. And this is the number of electronic components we're going to observe on the third day, which can also assume these values, okay, in that order. So we can see that we now have a collection of random variables. We have 1, 2, 3 in that order. So this is going to be a collection of random variables. So we can say that this X index T is a stochastic process, okay? Similarly, I can represent this scenario using a different approach. So let's assume that I have my time factor or my index set on the x-axis, and I have my possible values on the, as my possible values, right, of the process on the y-axis, okay? So let's assume that on the starting day, the number of components that are defective is 0. On the first day, it was 1. On the second day, it was 0. On the third day, it was 2, in that order, okay? So this is just a single realization or a single sample path, okay, of the process. So when we talk of realization or sample path, it is also known as sample function. It is just the individual time function that of the random process, okay? So the individual time function of the random process that we just observed here is the sample path or the sample function or the realization. Let me quickly show you what I mean here. So this is a sample function, okay? This is a notation of random process. So this line that you see here is a sample function. This is also another sample function. This is another sample function. A collection of sample functions is known as ensemble, okay? So what we have here is just a single realization of the process. If you have to repeat the experiment, it could be that on the starting day, the number of electronic components that are detected was 1 or 2. On the first day, it could be any possible value that we have here, okay? So the intuition, let me go back. The intuition behind this realization or sample function or the sample path is that any random experiment is defined on a sample space. Okay, so after observing the values of the random process, we obtain a function of time such as shown here. Okay, so one thing that you have to note here is that if the sample averages formed from a single realization of a stationary process convert to some underlying parameter of the process, then we say the process is ergodic, okay? I'll explain what stationary process means in our subsequent tutorials, okay? So in other words, what I'm trying to say is, is that an ergodic process is a stationary process such that its time average, okay, the time average that we're going to observe is equivalent to the ensemble average, okay? So basically, in order to make inference about the underlying laws that govern an ergodic process, one needs to observe only a single sample function, but over a sufficiently long span of time, okay? So this is something that you just have to take note of. So let's go back to our slide and continue with the example. Now let n index t be the number of customers who visited a bank from time t, which is equal to 9. That is when the bank opens at 9 a.m. until time t on a given day, okay? Say from 9 a.m. to 4 p.m., okay? For 24 hours, we have 9 to 16, where t is measured in hours. So we can show that n index t is a stochastic process as follows. So in here, I have my index set on the x-axis, which is time in hours. I also have my possible values, that is the number of customers who are going to visit their bank on the y-axis, okay? So we can see that, let's assume that when the bank opened, the number of people who visited the bank were less than 10. So I have the point here. At time 10 a.m., the number of customers who visited the bank were between 25 people, okay? And also at time 11 a.m., these were the number of customers who visited the bank. Time 12, 13, 14, 15, 16. So this is just a single realization, okay? Now, because we have an index set which is continuous, time is continuous. So this is going to be how the sample path or the sample function or the realization will look like. So between 9 to 10 a.m., we can observe any of these possible values. Okay, so these are the number of customers who can visit the bank from time 9 a.m. to 10 a.m. The same applies to 10 a.m. to 11 a.m. You can observe all these possible values. These are the number of customers who come to the bank from time 10 a.m. to 11 a.m. And also from 11 a.m. to 12 p.m. we can observe this number of customers within the bank. Okay, the same um, illustration follows. Okay, so this is just a single realization. If you have to maybe observe this process again, the sample path or sample function will change. Okay, all right, so let's now jump into the second session and take a look at the specification of stochastic processes. So a stochastic process is specified by its state space and its index sets. Okay, so before we define state space, let's take a look at states. So when we talk of states, these are the values which the random process can take. Okay, for example, this value here is a state, 2 is a state, 1 is a state, and 0 is a state. Okay, so the values that the random process can take is going to be a state, okay? All right, so let's go back to our slide and now let's take a look at state space. So the state space is a set of possible values of the random process, often denoted by X, okay? So basically what we're trying to say here is that these values that we have here, the possible values of the states becomes a state space, okay? So 0, 1, 2 is going to be our state space, okay? We often use S for that, okay, to denote it, all right? Or let's say the possible value that you're going to observe here is going to be our state space, okay? All right. Now take note that if the state space is discrete, right, then we can say that we have a discrete state stochastic process. On the other hand, if the state space is continuous, okay, then our process is going to be a continuous state stochastic process, okay? So let me quickly go back. So here, because the values here is countably infinite, we have a discrete state stochastic process, but sometimes the value that you can observe here may be continuous. Okay, it can be 10.567 or it can range between 10 to let's say 50 or any value. Okay, so take note of that. All right, so now let's take a look at the index set or the parameter space. Now, if T is discrete, that is, it's a finite set or countably infinite set, then the process is called a discrete time stochastic process, and it is customary to use n instead of t, okay? So we replace t by n anytime we have a discrete time stochastic process, but you can use any, okay? All right. Now, if t is continuous, that is t is a semi-open interval from 0 to infinity, or t is a closed interval from 0 to k, where k belongs to the set of natural numbers, then we can say that the process is a continuous time stochastic process, okay? So if I go back and say that in here, this time, we have this time, so we have a continuous time stochastic process. Now if I go back to this side, I was trying to show you the other one where the index set was discrete, okay? So this is an example which is continuous. You can also have it to be discrete, okay, like the previous example. All right. So let's continue to the next session on classification of stochastic processes. So the first classification is the discrete state space with discrete time process. An example is the Markov chains. We have a simple random walk and we have the Bernoulli process. We already know what a Bernoulli process means, okay? So in our subsequent tutorials, we are going to take note of, we are going to take a look at the Markov chains and simple random walk, okay? Okay, so we will take a look at this classification in our subsequent tutorials, okay? The second classification is a discrete state space with continuous time process. And examples include continuous time Markov chains and Poisson process. Okay. The third classification is continuous state space with discrete time process. An example is the time series analysis. Okay. And the last classification is a continuous state space with continuous time process. Okay. Examples include the Brownian motion or the Werner process and Gaussian process. So we'll take a look at all this classification one after the other in our subsequent tutorials. Okay. All right. So now let's take a look at the last session on examples. So let's take a look at the first example. Desmond and Emmanuel play a coin tossing game. Desmond agrees to pay Emmanuel $5. Desmond and Emmanuel play a coin tossing game. Desmond agrees to pay Emmanuel $5 whenever the coin falls heads, and Emmanuel agrees to pay Desmond the same amount whenever the coin falls tails. Okay, so let S index n denote the amount n by Emmanuel in n tosses of the coin. Okay, so we want to determine the state space and the index set of this process. And secondly, if the coin is fair, we want to show that the expectation of this process is going to be 0, and also want to find the variance of the process. So let's take a look at the first part. All right, so you can see that our index set is going to be countably infinite, okay, and our state space is going to be finite, okay. So if you check this, we want to, our S index n is an amount n by Emmanuel in n tosses of the coin. So we know that for the first toss, you can also observe a second toss, head toss in that order. So the tosses is countable. Okay, so that's why our index set here is countably infinite. Our state space is also going to be finite, okay, because we know that anytime we toss a coin and it falls heads, Emmanuel is going to gain $5, and anytime it falls tails, Emmanuel is going to lose $5. So that's the minus. But anytime there is no toss, there's no amount, Emmanuel is not going to make any amount of money. So we have this state to be zero, okay? So basically, let me picture this for you. So let's say we have the index set on our x as axis here, that's the n tosses, and we have our the amounts that are going to be n on our y axis. Okay, so on the first at the initial stage, let's assume before the toss, Emmanuel is not going to make any amount of money, so the state space is going to be zero. So it is possible that at the first toss, it's landed in tail. So Emmanuel is basically going to lose $5. And it is also possible that at the second toss, it's landed head. So Emmanuel is going to gain $5. So this is just a single realization or a sample function of this process. Okay. So you can see that our index set is basically going to be countable infinite, and our state space is also going to be what? Finite. Okay, so that's basically what we have here. So we can basically say that our process S index n is a discrete state stochastic process indexed by a discrete time. Okay, all right, so let's take a look at the second part. In here, we want to basically show that the mean of the process is zero, and also to find the variance of the process. Okay, but before that, let x index I denote the amount in dollars n by Emmanuel in the ith toss of the coin. Okay, so we know that once we toss a coin and it lands in head, that's +1. Head is 4. Basically replacing head with +1. Okay, the probability is going to be 0.5. And once we toss a coin and it lands in tail, or it falls tails, we are replacing tail with -1, and the probability will be 0.5. Okay, so we can show that expectation of this type loss can be expressed in this form, which is similar to that. Okay, and we know that I assume you can do this based on our previous tutorial on expectation of a number of variables. Okay, we can express this in this form. Okay, so in order to find the variance, we have to obtain the second moment about origin, which can also be expressed in this form. Okay, so the variance can be expressed in this form. This is the second moment about origin, which is 1, and this is the mean. So once we replace these values, we obtain 1. Okay, so we can show that for I running from 1 to n, the expectation of this process is, it will be in this form, which will be 0. Okay, so for the ith toss, okay, for the ith toss, we know that the expectation on the process is going to be 0. So for the nth toss, basically is going to be 0. Okay, and for the variance of the process can also be expressed in this form, which is similar to n. Okay, because if the variance for the ith toss is 1, then for the nth toss, we are going to have n. Okay, let's take a look at the second example. Suppose 5 red balls and 3 black balls are placed in 2 boxes, B1 and B2, so that each box contains 4 balls. At each stage, a ball is drawn at random from each box, and the 2 balls are interchanged. Let y index n denote the number of black balls in box 1 after the nth draw. So I want to determine the state space and the index set of this process, y index n. And secondly, if x index n is the total number of red balls in box 1 after the nth draw, we want to determine the state space and the index set of this process as well. Okay, so let's take a look at the first part. So since the index set, right, t is going to be countably infinite, and the state space is also going to be finite, it follows that y index n, right, is going to be a discrete state stochastic process indexed by a discrete time. Okay, All right, so basically, let me try and picture this for you. So so let's assume we have let me go back first. So we know that we want to basically look at the number of black balls in box one after the end draw. Okay, that's this process. So the draws can be counted. Okay, we can have the first draw, the second draw, the third draw in that order. So definitely, or basically, our index set is going to be countable infinite. Okay, now with a state space, we have it to be 0, 1, 2, 3. How do you obtain this? So let me quickly show you that. So we have our two boxes here, box one and box two, and we have 5 red balls and 3 black balls. Okay, and they are placed in these two boxes such that each box contains 4 balls at the end of the day. Okay, now let's take for instance the first case. If we are to observe 4 red balls, it means that we are going to have 0 black balls, so that box one will have a total number of 4 balls. It means that the corresponding box two is going to have 3 black balls and 1 red ball. Okay, so once we add 3 plus 0, we have a total number of 3 black balls. And once we add 4 plus 1, we have a total number of 5 red balls. Okay, and each box will contain 4 balls. Okay, so we have 4 here, we have 4 here. Now let's take a second case where we are going to observe 3 red balls and 1 black ball in box 1. It means that we'll have 2 black balls and 2 red balls in box 2. Okay. For the third case, if we are to observe 2 red balls and 2 black balls in box 1, then we are going to have 1 black ball and 3 red balls in box 2. Okay. Now, for the last case, if you have to observe 1 red ball and 3 black balls in box 1, then it means that we're going to observe 0 black ball and 4 red balls in box 2. Okay, so these are the possible scenarios where we can have this process. So our random variable or our stochastic process is basically the number of black balls in box 1 after the nth draw. So for any draw, we can have 0 black ball, 1 black ball, 2 black ball, or 3 black balls. Okay, so we have 0, 1 black, 2 blacks, or 3 black balls. Okay, so that's basically why we have our state space to be in this from 0, 1, 2, 3, which is discrete. So basically the process is going to be a discrete state stochastic process of index by a discrete time. The time index is going to be discrete. Okay, now let's take a look at the second part. Okay, let me quickly take a look at this question again. So here, x index n is the total number of red balls in box 1 after the nth draw. So basically we know that the time index, sorry, the index set or the parameter space is also going to be countably infinite, because we can have we can observe the first draw, the second draw, the third draw, and that's order. So it's going to be countably infinite. Okay, so how do we obtain the state space? Okay, so using a similar approach, so we are going to have these possible cases. Okay, so we can observe 4 red balls after the nth draw. Okay, in box 1, we can also observe 3 red balls, 2 red balls, and 1 red ball. Okay, so that's basically what we have here. So we can have the time, the index set to be countable infinite, and our state space to also be finite, 1, 2, 3, 4. Okay, so therefore we can say that x index n, right, this process is going to be a discrete state stochastic process indexed by a discrete time. Okay, all right, so now to the third example. Consider the number of telephone calls received at a telephone exchange at time t. Want to determine the state space and the index set or the parameter space for this process. Okay, so let's take a look at the solution. Let x index t denote the number of telephone calls received at time t, such that the process can be defined in this form. So we know that the number of telephone calls is something that is countable, so the state space is going to be discrete, and now our index set is time, so it's going to be continuous. Okay, so we can say that x index t, this process is a discrete state random process indexed by a continuous time. Okay, let me show you how this will look like. So we have the number of telephone calls on our y-axis, and we have our index set on the x-axis. Okay, so from time 0 to time 1, we can observe any of these number of telephone calls. This is just a possible realization or a sample function. Okay, from time 1 to time 2, we can also observe this number of telephone calls in that order. Okay, so this is how it will look like. So our index set is going to be continuous, and our um, state space is going to be what? Um, countably infinite or discrete. Okay, so that's why we have our state space to be a discrete state random process, and our index set is continuous time. Okay, all right, so now to the last example. You have $1,000 to put in an account with interest rates are compounded annually. That is X index N is the value of the account at year N. Okay, so we can have our process defined in this form. The value of the interest rate, which is R, is a random variable. It's a random variable that is determined when you put the money in the bank, but it does not change after that. In particular, we assume that R, that the interest rate is uniformly distributed with a lower value of 0.04 and an upper value of 0.05. Okay, so basically we can say that the interest rate ranges from 4% to 5%. Okay, so we want to find all possible sample functions for the random process. And second, we want to find the expected value. We want to find the expected value of the account at the third year, which is the expectation of this process. Okay, so let's take a look at the first part. So let our interest rate, capital R, be equal to a particular value R. Then we can have our process defined in this form for all years. Then the sample functions can be defined in this form. Okay, so once we try to replace this interest rate with any of these values in this range, we are going to observe some realization or sample path. Okay, so this is how the sample function will look like for any year, for year 1, for year 2, for all years. Okay, this is how the sample function will look like. But once we try to replace this interest rate with any of these values within this range, we are going to observe a sample realization or a sample function or a sample path. Okay, all right, so now let's take a look at the second part and go back and check the question. So we want to find the expected value of the account at the third year. So the process at the third year can be defined in this form. Okay, and if we are to replace 1 plus R with Y, then we can have the process defined in this form, where Y is uniformly distributed within this range 1.04 and 1.05. Don't forget that R is within the close interval from 0.04 to 0.05. So once you add 1 to it, you have 1.04 and 1.05. Okay, so we can have the density function with a uniform distribution being displayed in this form. Okay, so if you don't know how the uniform distribution looks like, let me quickly show you. So this is the density function of the uniform distribution. We have 1 divided by the upper limit divided by the lower limit. Okay, and this is the cumulative density function with the main function, the variance, and the moment generating function. Okay, so similarly, we have if you try to have 1 divided by this minus that, okay, you're going to obtain this. Okay, so we want to find the expectation of the process at the third year, which can also be expressed in this form. And I know you know, and I guess you know how to do this based on our previous tutorial on expectation of random variables. Okay, so we can basically express this in this form. Okay, which can also be expressed in this form once we take the integral, and once we try to input the values to obtain this, and once we try to multiply through, we are going to obtain this result. Okay, so this is basically going to be the end for this tutorial. Please, if you find value into this tutorial video, don't forget to subscribe if you have not. And thank you for watching. Okay.